All right, chemistry time. We're going to talk today about, the title of this first lesson is called Light and Quantized Energy. We're really talking about electrons and the electromagnetic spectrum. Something that I've been personally thinking a lot about lately, I mentioned in my video I made this morning for 8th grade science, and it's really what this is about, but this is becoming, in more than just the educational and scientific parts of my life, it's becoming apparent that a lot of the universe operates this way, and it has been almost revelatory to me, but the universe, when you get down to it on the quantum mechanical level, which this class is not quantum mechanics, but we cannot discuss modern chemistry without talking about the idea of quantum mechanics. But when you get down to the quantum mechanical level, everything in a very real sense, the evidence suggests that everything is force fields and excitations within those fields, waves. Everything is waves. You think of this as matter, right? You think of this as matter. I think of this as matter. In our daily life, we don't get much done if we don't think of stuff as matter, as just macro scale objects. But let's draw our atom. This is how, remember from the last lesson, that we used to think about atoms. Remember that? This is kind of like the Rutherford model of the atom. I mean, you remember this a little bit. You don't need to write this down because this is not good. This is bad. We don't use this anymore. It's not a ball, and it's not electrons, other little baby balls orbiting it in circles. We know that it's not that. We know that it's not that because I told you that, which I learned from the book. But the evidence, the real experimentation, suggests that this is not the case. One piece of experimentation that suggests this is not the case is the cover of your book, which I have my book covered, but you remember from physical science the flame test. You remember the flame test? Where you take some metal salt, barium or copper or magnesium, but you take some salt of those, barium chloride, magnesium chloride, etc., and you put them in the fire in a different color. You remember that? What that tells us, and it doesn't seem like that would provide a piece of evidence that this doesn't work, but what that tells us is that the electrons, I've already said this phrase too much, but in a very real sense, in a sense realer than this podium, or realer than the whiteboard, in a real sense, the electrons exist as waves. They are energetic waves that are, when they become energized, have a certain frequency to that wave, and then when they become energies, when they go down energy level, they emit that same frequency of light, which we see, your eyes, your little eyes, that Rhett is rubbing because he's tired of me talking already and we're only 2 minutes into it. I'm just kidding. That's probably not true, Rhett. That's probably not true, Rhett. But your eyes are programmed to perceive different frequencies of light as color. So when we see that the copper emits a different color of light when it's heated up from the sodium, for instance, that tells us that that's real physical proof before your eyes that these electrons are existing in some way as manifestations of a field, as waves. So what this really is, erase this. This is trash. Is it trash? No, it's what do we call it when it's almost trash but it's still helpful? Do you remember? Model. Yeah, it's a model. It's a model. We know that there are shortcomings to it, but it does. Like if you were talking to a kindergartner, that model of the atom would be very useful because you could show them, here's the nucleus, and here are some electrons. They're outside. They're away from the nucleus. They're separate things, right? That would be helpful to them. And then you get a little bit older and we realize, well, it's not quite like that. And this is like the whole story of your education. Elementary school is like, here's how it be. And then in middle school, you're like, well, it's not quite like that. They're not wrong. It's just not quite like that. And then high school is like, well, it's actually much more nuanced than that. And then you go to college, they're like, actually, it was wrong. Your elementary school has nothing to do with reality. This is the way it really do be. And one of the ways it really do be is that what's really going on is the entire universe, which I'm going to represent here with an oval because of models. The entire universe is permeated throughout it, all of the way. Every single microscopic, what we call Planck length. You learned about the Planck constant in your vocab, I think. But a Planck length, the very smallest little piece of the universe is permeated with 4 fundamental force fields. What are the 4 fundamental force fields, if you had to guess? In order of strength. And in inverse order of range. You probably already know them. Which one? We're going to start at the top. The strongest. Strong nuclear. Strong nuclear force. I'm going to spell nuclear correctly if I can. Electromagnetic force. How do you know these? You're just making these words up and they happen to be true, like Gandalf? No. You already learned it. You know the 4 fundamental forces of the universe. You're just now learning that they permeate the entire universe. Well, that's one of the reasons we call them fundamental. Weak nuclear. And gravity. And this, as a model, is bordering on metaphor. What I'm telling you is true of the universe, but it's also a model. We're not going to be actually observing these things. The whole universe, this nice oval, is permeated by this. I should have done these in a different color. The strong nuclear is going to be purple. Let's have electromagnetic be green. It's going to be the stupidest looking diagram. Weak nuclear force is going to be red. And then let's do the really hard to erase orange as gravity. And then this model is simplified to the point of uselessness, because what am I going to show is happening with the entire universe if these are permeating the entire universe? Hello, Lily. Oh, thank you. Place it there. Or do you want my approval of it? I approve.
Okay,
Bless you.
It's $10.
Can you take it back downstairs real quick, and then I will take all. Okay. Okay. As I said, this model is going to be simplified to the point of uselessness, because if I say these things permeate the entire universe, how should I correctly diagram that? Well, I'm going to. The whole universe is them. So you're tracking with me, though, right? This is so far making sense. None of this seems so esoteric or crazy yet. This is the universe. This is the entire universe. This is not. This is a model of the entire universe. Do I seem like a crazy person yet? I'm acting a little bit like the guy with the pictures and the strings between the pictures, like I'm having a psychotic break. But this is the truth. This is the real world. This is the universe. Everything is this. It almost like an illusion seems like it's eraser and shark poster and light and podium. But this is not the model, but this idea is realer than those things. Because what this is, well, if we get on the submicroscopic level, we get on the atomic level, and we look at podium, we realize, turn your books with me real quick to page, it's way in the beginning, and I'll show this picture on the screen too. I won't do it the fancy YouTube way where I have an actual picture that I've looked up come up, because I don't know how to do that, or I could probably figure it out, but I'm not going to, and I'm just going to keep looking and looking and looking in the book for it. Okay, I'm still looking. You're great. Yeah, if I could describe it, it would help you help me find it. It's like the scanning tunneling microscope image of the atom. Do you know what I'm talking about? It's in here somewhere. There it is.
Wait, hang on. I bet I can find it.
Okay, it's on page 107, at least in my text.
Yeah. The cool looking infrared.
Okay, so first of all, this is evidence. But evidence of what? Is this what an atom looks like? I'm going to put that in quotes, but I have my book held up. Is this what an atom looks like? Well, atoms don't look like anything because, as you remember from your bell work, the electromagnetic spectrum is a wave. And the wave that makes up visible light you can see, light that things look like, is a certain wavelength, but atoms are smaller than that. So atoms can't look like anything in the same way that blue eraser looks like blue eraser. But what does it look like? A little bit. A little bit. It reminds you of the crazy guy up front talking about this. What does it look like a little bit, that diagram? Does it? Does that look like? What does that look like? A little bit. If you squint and look at it sideways.
You know the word, but I can't think of the word.
Yeah, it looks like it is waves, right? It is waves. It is waves. It is waves, and that's what quantum mechanics is all about. That is quantum mechanics. Let me write that down. Quantum mechanics. That's the title. The tagline is, "It is waves." That's it. That's not it. It's certainly more nuanced than that, but it's mathematical. What's truer? We're getting to real philosophy here. What's truer? This paper is yellow or 2 plus 2 equals 4? What's truer? What's more universally true? I don't know. You tell me. I would say, I know what Mr. Stinley would say, and I would say it's the math. The math is truer. You could take this to someone another human being who doesn't have an understanding of what we call color, or I mean, like, different words for it, and you could say, this is yellow, and maybe even other languages don't have the names for colors that we do. What's his name? Who wrote the Odyssey? Homer. In the Odyssey, writes about the wine dark sea, because to the Greeks, red and blue were the same color because they didn't really have a word for blue. So people without a word for yellow, this is not that true. But 2 plus 2 equals 4. Even if they don't understand the words 2 plus 2 equals 4, you got 2 fish and 2 oranges, and that's 4 things. That's a fundamental truth of the universe. There are 4 discrete things. It is waves, is mathematical. There are mathematical models that show that this is the way the universe is. One of them, very simply, is given to you in your chapter, the de Broglie equation. Let's write down the de Broglie equation real quick. This is really starting to sound like a rant, and I apologize for acting like a crazy person, but the de Broglie equation, this is probably the simplest equation from quantum mechanics. De Broglie equation is lambda representing what? Lambda is what? You remember from physical science, hopefully. Wavelength. And in what units do we measure wavelength? Meters. Usually meters. In the SI, we measure them in meters. This fancy H is, you should know from your vocabulary, fancy H? Anyone? Bueller? Bueller? You don't get my reference? No. Okay. Ferris Bueller's Day Off. Yeah, I've gone from crazy guy at the board to the boring history teacher who can't get people to answer his questions. This is.
Don't tell us. Fancy H. Hang on. Planck's constant.
Planck's constant. Named after Max Planck. Planck's constant. And not only does Planck's constant have a unit, which it does, but it also has a value that you need to memorize. And Planck's constant's value is 6.02 times 10 to the negative 34th joule seconds, I believe. I'm trying to look it up in the book to make sure I haven't lied to you. Oh, 6.626 times 10 to the negative 34th joule seconds. Sorry. 6.626 times 10 to the negative 34th joule seconds. So this has a known value, not just a unit, but it has a known value that you have to have memorized. 10 to the negative 34th joule seconds. What's m, probably? Usually. Lowercase m as a variable, not as a unit. Mass. Measured in kilograms. It has to be kilograms for this to work out. And then nu is, you remember? That's the Greek letter nu, by the way. Oh, I'm sorry, no it isn't, it's v. Forgive me. V is velocity, measured in meters per second. And you can probably, astute observers or analyzers of dimensions will realize that joule seconds divided by kilograms divided by meters per second gives us meters. Because a joule is equal to a kilogram meter squared per second squared. Times second is a kilogram meters squared per second. Times this second is a kilogram meters squared. Then times this meters cubed, divided by this meters, divided by this meters is just, that's what we're trying to find is meters. The math works out. I really took my crazy pills at lunchtime, forgive me. The math works out. It'd be easier if I showed it this way. This is joule seconds, which is the same as kilogram meters squared per second squared times seconds. This one is meters per second, and this one is kilograms, right? So you can see since those are on the bottom of the equation, the kilograms reduce to 1. 1 of the meters reduces to 1. 1 of the seconds reduces that to 1. This second reduces the other 1. Since this thing was this, that's all reduced out except for the meters. So we're left with just meters over here. And what this equation tells us is that everything that has a mass and has a velocity has a certain frequency. You can calculate this. It's borderline meaningless, but you can calculate this for a soccer ball. You have a soccer ball across the room. You can calculate its frequency with the de Broglie equation.
What's underneath of it? Is that square?
Is what a square?
S squared.
Yeah, yes. But everything is waves. Let me see if I can bring it back to what we were talking about before. This is the universe. A really good model of the universe where it's just a mess of these different colors. A really good model of the universe. If we look at the microscopic scale of my podium like I promised we were going to do, we would see submicroscopically that instead of what we think of as a proton, what it actually is this is the electromagnetic force field. I'm going to draw it as a straight line. Does what we call a proton excite the electromagnetic force field? Let me rephrase it another way. Does it interact with the electromagnetic force, a proton? Yes, it has a what charge? Positive. So we're going to draw that as a positive excitement in the electromagnetic force. Does it interact with does it interact with the weak nuclear force? Yes, it does. Remember that in beta plus and beta minus decay, a neutron can turn into a proton and vice versa. So it does excite the weak nuclear force. Does it excite strong nuclear force?
Yes.
Yeah, it does interact with the strong nuclear force, so it excites that one. Does it excite gravity? Well, what's the dependent thing on gravity? What physical property of the universe depends on gravity is mass. And so it does excite the gravitational force field that permeates the universe. So really, proton is not like a miniature basketball that has a positive charge. It is an excitation in all 4 of the force fields of the universe. What about an electron? Well, let's do that one next. Here's our little electron, which we classically draw as just a tiny ball, a baseball, I don't know. Does this make sense, though, that they're really not these physical objects in the same way that golf ball, baseball, basketball are physical objects? They're excitations in this force field. So it's not just a tiny little ball. Does it excite the strong force?
Yes.
Is the region where this electron is exciting the strong force?
Yes.
No. The electron does not excite the strong force. What do I mean by that? I mean that the electron does not interact with the strong force at all. Remember, the strong force, it holds the nucleus together. That's what we said last time. And that's a more basic thing to understand. But what I'm getting at here, the real universal basic, the thing that's harder to understand, but actually the truth about the universe, is that it just doesn't excite this strong force field. What about the electromagnetic force? Does it excite that? Yes, but in the opposite direction that the proton did. Does it excite the weak nuclear force? No, it doesn't. Not to my knowledge. Don't quote me on that one. I would have to look at the research. Does it excite the gravitational force field?
No.
Very barely. Almost 1/2000th as much, there we go, as the proton does. And we could do the same for a neutron. But when we get even further down, what's actually happening here is that these quarks that make it up are themselves exciting these force fields. Everything in the universe is just excitations in a force field. Electrons, we're going to get to in a second here. Electrons, when they are more excited, is anyone still writing this stuff down? This is kind of a conceptual thing that is not really going to be tested over. I just wanted you to have an understanding of what I mean when I say that it is waves, that everything is waves. The de Broglie equation tells us that everything is mathematically a wave. Does this kind of make sense? It does not supposed to hold. It doesn't make whole sense to me, but does this kind of make sense? Yes. Okay. This is philosophy. I mean, it's quantum mechanics, and it's science in the sense that it is true of the universe, but it's really more of a thought experiment, a way to think about things. Things are not as they seem. Well, let's move on to some nice, easy math to have for dessert. Do you remember the electromagnetic spectrum? Yeah. You should remember from physical science. You should remember it from your bell work. One of the reasons I had you do it in your bell work is so that you would remember it from physical science. That was a really good drawing of the universe. There's an electromagnetic spectrum. Very briefly, the properties on the electromagnetic spectrum are wavelength and energy or frequency. They're all what, though? What's everything on the electromagnetic spectrum? They're all kinds of light. And light has a certain speed. C is what we use to represent the speed of light. C actually stands for constant because the speed of light is constant. And it's 3.0 times 10 to the 8th meters per second in a vacuum. Actually, it's that speed everywhere, but if it's not in a vacuum, the particle interactions that it commits to on the way cause it to, on average, slow down. There are interaction times. And it really isn't even about that. It's more like the path that it takes because it is compelled to interact with particle after particle becomes more jaggedy. So just because it takes longer to circulate this path than this one, the speed of light apparently, not realistically, but apparently slows down when it's not in a vacuum. So we have this equation, C equals lambda nu, where C is the speed of light in a vacuum. Is this hard for you to read in real life or just on the screen? Okay, I'm sorry. I'll switch colors after this one. Speed of light in a vacuum, which is